Good morning students. Today is the module 2 and lecture 5. So, here in this class we will cover about the membrane modules and different types of membrane modules and what are the flow types and then how we actually select particular module. So, you know large membrane areas are normally required in order to apply membranes on a commercial and industrial scale. Membranes have to be assembled in units that are compact and at the same time spacious. Now, these membrane assemblies are actually called as membrane modules. Now, module by definition is the smallest unit into which the membrane area is packed. Whatever may be the membrane area, that what you actually we get after we perform a particular design to achieve a target separation, and the module is the central part of the membrane installation. The simplest design is the one in which a single module is used. Now, there will be an inlet for the feed and outlet for the permeate and retentate. That is the most basic membrane module that can be possible. The permeate stream is the fraction of the feed stream which passes through the membrane, and retentate is the one which is retained on the surface of the membrane. Please look at this particular figure and you can see a feed inlet stream enters the module at a certain temperature, pressure, concentration and flow rate. Now, the feed composition and the flow rate inside the module will change as a function of distance, right. So, that precisely that means that when the feed is flowing like from the inlet to outlet in this direction, okay, the composition of the feed as well as the flow rate will change, because the membrane the feed is passing through the membrane. So, some permeation is happening and then whatever the solutes that are not able to pass through the membrane are retented. So, the solute concentration on the surface of the membrane which are rejected is getting enhanced as the flow progresses, and as the solutes which are rejected through the membrane, that means they are going to this permeate side, okay, their concentration in the feed is continuously decreasing. So, the feed stream then further separates into this permeate and retentant streams depending upon the feed composition and the membrane properties, and the feed components that are allowed by the membrane to be passed through form the permeate stream, and the ones that are not form the retentant stream. This is what we have understood earlier also. Whatever that is rejected by the membrane, or we can say retained on the surface of the membrane, okay, that forms retentate. Whatever that is passing through the membrane, okay, that is permeate. So, let us start discussing the module configurations. There are various types of module configurations that is possible, where broadly we classify them into two types: flat sheet or disc type, under which the traditional plate and frame module and spiral wood module will come, and then hollow fiber or tubular, under which tubular modules, hollow fiber modules, capillary modules, all these are the possible configurations under hollow fiber or tubular category. So, this is the flat sheet plate and frame type flat sheet or disc type membrane, which is the traditional plate and frame module, and here this one is the tubular or hollow fiber module. So, if tubular hollow fiber membranes are packed close together, okay, in a parallel fashion, then membrane area per volume is only a function of the dimensions of the tube. So, that means when the fibers we can have single hollow fiber membranes or fibers, we can call them fibers also. So, many of them actually are joined or fused together to form a hollow fiber membranes module. The membrane area per volume is usually a function of the dimensions of the tube. So, you increase the dimensions of the tube, your membrane area per volume gets increased. So, you can see the approximate dimensions of tubular membranes. So, tubular is usually greater than 10 centimeter 10 millimeter, capillary is 0.5 to 10 and hollow fiber is usually less than 0.5. So, the membrane surface area per volume is a function of the radius of the tube and clearly demonstrates the difference in the membrane area per volume per tubular system. Usually, the radius is about 5 mm and hollow fiber system it is anyway between 50 micron to 0.05 mm, that is basically. So, that you can see the table 2 where we have given surface area per volume of some of the tube radius. So, if the tube radius is approximately 5 mm, so you get a surface area per volume is almost approximately 360 meter square meter per meter cube. Similarly, for 0.05 we get 36,000 area per volume, that is meters cube per meter cube. So, in general a system does not consist of just one single module, but of a number of modules arranged together as a system. Now, each technical application has its own system design based on specific requirements. Now, please understand that whether I am going to use a single module or I can have so many different modules which are fused together or combined together. So, it all depends upon what is my targeted separation, what I want to achieve, what is the fluid, what I want to retain, what I want to permeate, and there are so many other process parameters that also affects as apart from the membrane itself and as well as membrane module configuration. So, we have two basic types of design. So, one is called the single pass system and another is a recirculation system. So, in single pass system, so you can see this one single pass system, here the feed enters, okay, and the permeate is that is coming through the membrane and we get retented here. And in case of the recirculation system, okay, so feed that is entering the membrane module, permeate we are getting here and we are getting retented here, but the part of the retented is getting recycled back. Okay. So, this is called recirculation system. This is actually being done to achieve a particular separation or target oriented separation. Okay. The choice of module configuration as well as the arrangement of the module in a system depends on several characteristics features. So, the first and foremost important thing is of course cost. Cost is the most important thing. Then type of the separation problem, what you are going to separate, that is very important. Okay, you may be given a task of separating or purifying water, it may be desalination, okay, of brackish water or sea water. So, it can be removal of organics or heavy metals from wastewater stream, or it can be purifying proteins or monoclonal antibodies. So, the list is endless. So, that is one of the most important consideration while deciding a module configuration. Then ease of cleaning is one of the another parameter which also should be considered while designing a module. How easily I can clean a membrane, because anyway after certain time either time progresses or time elapsed. So, what will happen that there will be concentration, polarization and fouling. So, to get rid of these things we need to clean the membrane either by using backflashing or some other techniques. So, to do that I must disassemble the membrane module, and module should be in such a way that is easy to assemble and easy to disassemble, then cleaning will not be a problem. So, ease of maintenance and operation, so and ease of compactness. So, how compact it is in a small area, how much area it is actually occupying, in industry space is also a concern. So, in a less area, less space that is available, floor space basically, how can I configure a module so that in a less floor area I can have more membrane area. Then scale and possibility of the membrane replacement. Now, students, let us see one by one different types of configurations. The first most important membrane module configuration that has been actually discovered is nothing but the stir cell module. So, you can see the picture exactly it looks like this. This is a dead end filtration module, and it is called stir cell because there is a stirrer here inside which is not visible. Okay. So, it is mechanically it is getting stirred here also. Okay. So, I can have a mechanical stirrer from here, or I can have some a magnetic stirrer here, okay, and have a magnetic plate here. So, that the module will be stirred. So, the material inside the module will be stirred. So, these are useful for small and research applications, usually lab scale. No, there is no commercial application of this in large scale operations, commonly used to characterize actually microfiltration and ultrafiltration membranes. So, they provide the beauty of this module is that they provide uniform transmembrane pressure and hydrodynamic conditions at all points of the membrane surface. That is because it is a dead end filtration and batch type. You feed the module, then close it and stir it. So, then separation is occurring. So, continuously permeate is being drawn out, okay, and however, the retented and the feed remains inside and above the surface of the membrane, okay, and the effects of process parameters on process efficiency can be very easily determined, hence useful for small scale process development work. These are not of much use in intermediate and large scale. So, basic use is that let us say you design a membrane and you fabricate it. So, then you have to test the membrane. So, to testing that membrane and finding out its performance in the lab scale, actually it is being used. The next one is plate and frame module. So, actually these are also called flat sheet tangential flow module. So, in many books you will see that it is called TFF system or TF systems or TF modules. So, what happens actually here, the sets of two membranes are placed in a sandwich like fashion with their feed sides facing each other. So, you can see here in this particular scheme, here the top portion is also membrane, here the bottom portion is also a membrane, and what is provided here is a spacer. Okay. The spacer is a support screen, actually it is a support screen. Which is dividing the feed and permeate compartments into two separate divisions. The units may have square, rectangular or oval cross section. So, you can have either a square plate and frame module, or we can have a rectangular TF system, or we can have a oval cross section TF system also. The packing density, which is nothing but the membrane surface per module volume of such module, is about 100 to 400 meter square per meter cube. So, you can see this is another figure here. Here the feed is entering here, okay, and we are getting the overall retentate here. So, you can have so many different types of membranes arrangement here, okay, and the permeate we are getting here. So, actually this is one of the oldest type of system, and quite good also, and in order to reduce channeling, the tendency to flow along a fixed pathway and to establish an uniform flow distribution, the stop dish or baffles have been introduced. So, please look at this particular figure. So, you can understand that. So, there is a baffle here, right. This is also called stop dish. So, this is being introduced, okay, and to separate two different compartments. So, this is one particular section, this is another section. So, we can have more sections here also, we can add on more sections. Okay. The spacer materials are used to improve mass transfer and to reduce concentration polarization. So, you can see how the flow is happening actually. So, feed is coming here, okay, and then it is entering here, here and here and here, okay, and again that is getting circulated here, then again coming to the second compartment. Again the feed is flowing through from the top here, and we get overall concentrate or retentate here, and we will get the permeate here. Okay. This is the permeate channel. Okay. This is these are membranes. So, this is a membrane, this is another membrane. Similarly, this is a membrane, this is a membrane. What you are seeing in the cross section actually, so that is actually the permeate channel with spacer, that is the spacer and the place for the permeate to flow through. So, in electrodialysis, special stack designs are applied mainly based on two concepts. One is tortuous path and another is sheet flow. So, the tortuous path has been developed by applying a proper spacer material for reduction of concentration polarization. The aim of developing this tortuous path is to reduce the concentration polarization. So, as to minimize fouling, by applying a high cross flow velocity, the residence time of the feed in the feed channel would be quite low. So, a gasket is used to transform the flat plate into a long tortuous narrow channel. So, you can see how the flow is happening. So, feed is coming here, okay, it is going here like this in a circular motion. So, that is why it is called a tortuous path. So, since and we have this baffles here, okay. So, these baffles are providing to the tortuous or helping that establishing the tortuous flow. Okay. So, if the flow will be like this, then the concentration polarization on the surface of the membrane will be minimized. So, that is the aim to have such type of flow. So, the advantages of such modules, which is the TF or plate and frame module, is that so they provide good flow control on both permeate and feed side of the membrane, and they can be easily disassembled. So, this is one of the most important thing while designing the module actually for cleaning and replacement of defective membranes. So, they have the ability to accommodate low levels of suspended solids and viscous fluids. This is also important because in many times it may happen that the levels of suspended solids are very low, and so that other module configurations may not help it. So, in that time we can use plate and frame type, and if the fluid or the feed viscosity is very high, then we can use plate and frame module. However, they have so many disadvantages also. The first and foremost disadvantage is large number of spacer plates and seals are required. So, we are complicating the flow design actually, basically the flow path. and leakage through the gaskets. There are so many gaskets that is being utilized for this type of membrane module. So, that is why you have to take sufficient care, so that there is no leakage, but instead of that also pressure gets developed inside the membrane module. So, leakage happens, and the packing density is very less compared to other types of modules, and flow pattern and pressure drop distribution is very difficult to characterize, and the cost of the module is actually high. So, the applications are they are used in electrodialysis and electrochemical systems. Apart from nowadays, they are also being utilized for the pervaporation system also. Have there limited number of reverse osmosis and ultrafiltration application is there, but there another important thing I forgot to mention early slide is that they are very useful for highly fouling feeds. It may happen to them sometimes the feed contains certain solutes, so which are very highly foulable. So, that time actually this type of module will help us. Students, the next one is the spiral wound module. So, spiral wound module is the next logical step from the flat sheet membrane development. So, it is in fact a plate and frame system wrapped around a central collection pipe in a similar fashion to a sandwich roll. You can imagine there are so many flat sheet membrane modules, and I am wrapping them on the surface of the tube. So, that is how actually spiral wound looks like. I will show you a figure in the next slide. So, membrane and permeate site spacer material are then glued along 3 edges to build a membrane envelope, and the feed side spacer separating the top layer of the two flat membranes also act as turbulence promoter. Here there will be spacer in the feed side also as well as permeate side also, and the feed side spacer is acting as a turbulence promoter. So, basically spacers are screens or meshes. Okay. Maybe either of stainless steel or any other metals and alloys, and the packing density is greater than that of the plate and frame module. So, packing density is higher than that of the tangential flow systems, but depends very much on the channel height, which in turn is determined by the permeate and feed side spacer material. So, let us now see how it looks like. Okay. You can see this particular figure. So, you can see there is a tube here, this tube. Okay. So, you can imagine that so many of membranes materials as well as this is the membrane, okay, and this is the feed spacer space. Then there is another membrane here, this is another spacer here. So, a feed spacer, a membrane, a permeate spacer, another membrane. So, they are all glued together and rolled on a particular tube, which may be this tube, okay, perforated tube of course, and this is being prepared actually. So, the feed flows axial through the cylindrical module parallel along the central pipe, whereas the permeate flows radially towards the central pipe. So, feed is flowing like this, okay, in this direction, right, and we are getting concentrate out here, whereas here permeate is getting collected through this particular tube over which the membrane and the spacers are actually rolled on. So, here the presence of spacer has a large influence on the mass transfer and the pressure drop. The feed and permeate flow patterns are very complex, because you can understand this is a very compact system, and the beauty of the system is that in a very less space we can have more membrane area, that is the only thing. However, the flow type are very complex and difficult to characterize. So, module is placed inside a tubular pressure vessel usually. Okay, number of spiral wood modules are assembled in one pressure vessel and are collected via the central permeate tubes. So, fluid solution passes across the membrane surface, a portion passes through membrane and enters the permeate site. This is actually the cross section of the spiral wound membrane. Okay. So, the arrows indicate the permeate flow. So, you can see these arrows, this is an arrow, this is an arrow, this is a radio, this is how the permeate is getting collected, okay. And these are actually feed spacers, okay. And this is the permeate collecting tube, okay. You can see in this particular figure here, this is spiral wound module arranged in series. So, you can have separate more than one spiral wood membranes and then place them in series. We can call them either in series, many times we call them cascades also. So, this is what it is actually, cascades. Here in this particular figure we can see there are three systems or three spiralude modules. So, in this particular figure these are RO modules actually. So, it can be anything, it can be UAP, MAP or any other systems. Okay. So, feed is entering in one place here, then it is passing through the membrane and we are getting permeate from the central collection tubes. Okay. So, these are the tubes which is collecting, okay, permeate, and then we get concentrate here. So, the advantage here is this, the more packing density compared to flat sheet membrane, that is what I told, in a small space I can have more membrane area and relatively cost is low than other membrane modules. A disadvantage is that it cannot handle high transmembrane pressure, because if the transmembrane pressure becomes high, pressure development will be built up in such a way inside the membrane module that it is not good for the separation, and you will not eventually get whatever the targeted separation. Then another problem is handling suspended solids. So, it cannot handle good amount of suspended solids and difficulty in cleaning and high temperature applications. So, since they are actually rolled on and they are glued to each other, so cleaning is a big problem, and then they cannot be used for high temperature applications also, because it happens many times in process industries, the water that is coming out of the, or the streams that is coming out of the various process units are at elevated temperature, needs to be separated or purified for certain targeted separation. So, in that time the feed will be at higher or elevated temperature. So, and you either you can cool the feed by passing through some silent tube heat exchangers and get the heat recovered for them. So, that heat actually is also in process industry, it is called waste heat recovery, where we recover the heat from the process streams, okay, and again use the heat in either form of steam or some other form to and supply it to other things, other units. So, they cannot withstand, this type of modules cannot withstand high temperature. So, the applications are widely restricted to nanofiltration to remove calcium or divalent ions from hard drinking water, desalination, the reverse osmosis arrow, which actually I show you the previous slide, and food industry in which ultrafiltration, usually the spiralude membranes are actually UF membranes, and gas separation applications in natural gas industries. Students, the next one is the tubular module. These are one of the most commercially adapted and industrially adapted actually technology. So, tubular membranes, unlike hollow fiber and capillaries, are not self supporting. So, they are not self supporting membranes. So, therefore, these membranes are kept inside a porous metallic, ceramic or polymeric tube. So, they are not self supporting. So, they have to be kept inside some support, which can be a metallic, ceramic or polymeric tube. So, inside this tube a number of tubular membranes that can be packed is not limited, and as much as possible can be packed in a silent tube heat exchanger type actually. So, in this module feed flows through the packed tubular membrane and the permeate passes through the wall and is collected in the cell via the porous supporting tube. The retented passes out the other side of the tube. Feed solution always flow through the center of the tube. So, you can see here. So, these things you are seeing na here, these are, so these are actually the tubular membranes, okay, and then here the feed is flowing, okay, here and here, right. So, the feed is actually entering or flowing through the center of the tube, okay, and we are getting the retented here, overall retented, okay, and the permeate that is passing through the membrane and passing out of the membrane basically are getting collected in the central space or the tube, okay, which is supporting these tubes, tubular membranes, and are getting collected here. So, this particular figure you can see, this is little more clear. So, feed is entering like this here, passing, okay, and then again it is getting circulated and coming here. So, we are getting overall retented here, okay. So, this is, since I told now, this is a cell and tube heat exchanger actually type, right. So, this is the cell side, okay, and these are tube side. So, we can have baffles inside also, right, and the permeate is coming here. So, these are the tubes, tubular membranes. So, ceramic membranes are mostly assembled in tubular module configuration because it is easy to fabricate also, and the tubular module is widely used for housing ceramic membranes with a packing density of 300 meter square per meter cube. It is a good actually packing density, not very high, not very low also. The monolithic module is a special type of ceramic module. So, I am specifically talking about ceramic membranes, tubular ceramic membranes and the module. Okay. Here a number of tubes have been introduced in a porous ceramic block. Okay. So, for an example, an alpha alumina, this is one of the ceramic membrane component. Okay. And the inner surface of these tubes are then covered by a thin top layer of alpha alumina or zirconia, for instance by a sol gel process. So, by making a composite membranes actually. So, you can see this is a monolithic module design. Okay. So, this is the feed channel, right. This is the membrane layer, top layer, and this is the porous support. Whatever you are seeing here, this is porous support. So, the advantages of using this tubular module is that the turbulent flow. Okay. So, why the turbulent flow is good? Because it is providing good membrane and feed contact, that is very important. The entire feed whatever that you are processing should come in contact with the entire membrane area that is available or that is being supplied through a membrane module, that only we will get a separation, that is what we are targeting actually. And not only that, so turbulence also helps in removing the retented buildup. That means, the solute concentration whatever it is developing on the membrane surfaces, if there is a turbulence flow, it will be lesser. So, and the cleaning is very easy in tubular membrane, easy in handling suspended solids and viscous fluids, okay, and ability to replace or plug a failed tube while the rest of the system runs. So, the meaning is that since we have so many, let us say because we have seen we have so many membrane modules here. Okay. So, these are all one membrane module. So, I am showing you 1, 2, 3, 4, 5, 6 here. Let us see this particular membrane is not working, it failed due to whatever, maybe it has broken or cracks developed or whatever it happens, so it is not work. So, I can either usually I can open the membrane module and replace this particular tube, okay, with a new one, or I can plug it. So, I can seal it from both sides, both end, okay, so that particular membrane module is not taking part in separation. So, that is why it is very important that this type of tubular systems are really advantageous when we are using them in industry or a large scale applications. So, feed flow pattern is easy to characterize, okay, and therefore, design and analysis based on fluid dynamics principle is also possible, can handle reasonably high transmembrane pressure, okay. And of course, with the use of, if you use a ceramic membranes, then the transmembrane pressure it can withstand more also. However, the disadvantage is that low packing density, the packing density, that is the membrane area per volume is less, capital cost is little high, and pumping cost that is required to pump the feed also is also relatively higher than other modules. The achievable concentrations, the targeted concentrations is also less. So, the next one is capillary module. So, the capillary module consists of a large number of capillaries assembled together in a module. So, you can see so many different so many capillaries here, okay, and the free ends of these fibers are potted with agents such as epoxy resins, polyurethanes or silicon rubber. Okay, the membrane are self supporting. Here we have seen in the tubular systems the membranes are not self supporting, however, here the membranes are self supporting, they do not need any intermediate support to hold them. Okay. So, feed is entering here as you can see, and we can get the overall retented here, and that permeates are getting collected out of the membrane, right, and we can get permeate here. So, two types of module arrangement can be distinguished for capillary modules. So, the first one is inside out, the second one is outside to inside. Let us understand what are these. So, the first one is the inside to out, that means the feed solution passes through the capillary or lumen, whereas the permeate is collected on the outside of the capillaries. So, the feed is passing through the membrane or capillaries and the permeate is getting collected here from the outside of the membrane. Whereas, in outside to inside is that the feed solution enters the module from the top. So, if you can imagine this is a particular cell, okay. So, the feed is entering from outside the membrane basically, right, and the permeate is getting collected from the inside of the membrane. So, the feed solution enters the module on the cell side, okay, and external, and the permeate passes through the membrane. So, inside the capillary the permeate is getting collected, right. In the first case the feed is flowing inside the capillary and permeate is getting out from the membrane from the outside from the external side. For the outside to inside it is the reverse. So, actually what type of this arrangements we are going to use or recommend. So, that depends upon the two concepts that depends upon the two things. The first is the application where parameters such as pressure, pressure drop, type of membrane available, all these things are important as well as the economics also. So, depending on the concept chosen, asymmetric capillaries are used with their skin on the inside or on the outside. And when porous ultra microfiltration membranes are employed, the capillaries mostly have a gradient in pore size across the membrane. So, in this case the location of the smallest pores inside or outside determines which type of configuration is used. So, usually the packing density is about 600 to 1200 meter square per meter cube is obtained with modules containing capillaries in between those existing and tubular and hollow fiber. So, basically in systems the packing density is higher than other ones, because since they are self supporting, they do not need any support, hence we can pack more and more capillaries inside a particular tube or a module. So that we will get more packing density as well as what is the overall membrane area increases. So, the advantages are capillary filtration sacrifices some of the rigidity gained from large structure for increased packing density. Okay. So, you do not have to go for a very large structure or very large system to achieve a more packing density. However, since they are self supporting, so in a smaller space we can have more number of capillaries fused together to have a better packing density. So, this offers some of the advantages about tubular modules where support and or durability are not key factors, right, and the packing density is greater than any other module. However, they also suffers from certain disadvantages. So, the problems which are regular actually in tubular membrane also they are the same in case of capillary modules, because the sizes are also very small here. Since capillary tubes are only slightly smaller, packing density is still an issue. Because of the decreased size as well, fouling is more likely to occur and rigidity and strength are not as high as tubular filtration units, because since they are self supporting and they do not have any external support, hence the strength is mechanical strength is basically is an issue. So, students, the next one is hollow fiber module. So, this is one of the most important development in the membrane technology. Here the difference between the capillary module and the hollow fiber module is simply the matter of dimensions, okay, since the module concepts are mostly the same. So, the hollow fiber modules, the feed solution can enter inside the fiber, either inside out or outside in. So, we can have two different configurations possible here, just like our capillary systems, and in reverse osmosis the feed mainly allowed either radially or parallel along the fiber bundle, whereas the permeate flows through the both side of the each fiber. The module configuration with the highest packing density can be achievable is almost 30,000 meter square per meter cube. It is a very high packing density. So, you can see here in this particular figure. Okay. So, the feed is entering here, right. This is a single module that is being shown here, right, hollow fiber channel. This is actually the membrane and permeate is coming outside the membrane, okay, and retentate is coming through the membrane. That means, from inside the membrane retentate is getting collected. So, this is actually inside out system. So, a more clear understanding picture you can see here. You can see how so many different types of hollow fibers are fused together, okay, and there is a tube here that is being shown as port, okay, and there is a port here. So, either we can flow feed from here, okay, or we can flow feed from here also. It depends upon whether you want for inside out or outside in, right. So, a perforated central pipe is located in the center of the module through which the feed solution actually enters. So, inside to out, in case of inside to out, the feed solution are more uniformly distributed throughout the module, so that the whole surface area is more effectively used. And in gas separation, the module will be always outside in. Why? Because it is being done to avoid the high pressure drop across the membrane. okay, and to achieve a higher membrane area. In pervaporation, it is more advantageous to use inside out. Let the feed flows through the membrane and the permeate will be collected outside the membrane. Okay, because you need to, many times in pervaporation system, to achieve pervaporation you need to vacuumize the system so as to generate low vapor pressure. So, we will discuss in pervaporation in detail in one of our subsequent lectures. So, that time it will be more clear that what is pervaporation actually. So, just for your understanding I am telling that we need to vacuumize the permeate stream in case of pervaporation, okay, so as to achieve our targeted separation. So, in case we are having out to in system, that time it is very difficult to achieve vacuumized. So, that is why feed flows through the lumen of the tubes and we get permeate outside. And another advantage of the inside out concept is that very thin selective top layer is protected, whereas in higher membrane area can be achieved with the outside in concept. So, if you go for a inside out concept and if you have composite membranes where the surface area is actually the surface layer is very thin and it should be protected, otherwise there will be wear and tear. Okay. So, then inside out is better, and if you want to achieve a higher area, then outside in actually better. So, there is no as such thumb rule what you are going to recommend. It all depends upon many factors. Okay. We have already discussed the factors. Then nowadays new module concepts have been developed mainly to reduce fouling and concentration polarization as much as possible, because that is the most important problem in membrane separation is the concentration polarization and subsequent fouling. So, to reduce concentration polarization as well as minimize fouling, so many new developments are coming every day. Now also membrane scientists are working to have a better module design. So, one way to achieve this is by changing the flow geometry. So, we can go for a transversal flow instead of a tangential flow. Okay. So, the feed flows perpendicular to the fibers, resulting in enhancement of the mass transfer in the boundary layer. So, feed is flowing perpendicular to the fiber. You can see how the feed is flowing here. Okay. And in the this is called, these are actually called transversal flow systems, in which hollow fibers or capillary membranes with top layer outside is a classic example, right. This type of arrangements are good for all pressure driven processes, whether it is microfiltration, ultrafiltration, RO process, as well as pervaporation and in liquid membranes also, and especially membrane contactors where boundary layer resistance plays an important role. Okay. In many membrane systems, the boundary layer resistance plays an important role. Wherever it is anticipated to play a greater role, because then it will provide a more resistance to flow, your separation will be drastically reduced. Then in such systems, we can go for this type of transversal flow instead of the tangential flow. So, in this type of module, the feed is flowing perpendicular to the fibers. So, this results in an enhancement of the mass transfer in the boundary layer, and fibers act in fact as turbulence promoters. As earlier also we have discussed that in one of the Platen frame time. So, when we are providing a feed spacer, so that is actually creating turbulence. So, here also the fibers themselves act as turbulence promoters. So, this type of module design is not only interest for the pressure driven processes such as microfiltration, ultrafiltration, RO, but also for any other system like pervaporation, liquid membrane and membrane contactors. Okay. So, you can see these are single hollow fibers. You can see this is one single hollow fiber, this is one, there are so many hollow fibers. So, they are joined together and form a module, and the modules looks like this. So, there are different types of system, a company makes its actual membrane solutions, and this here you can see. Okay. So, this is the plant. Okay. So, in this plant you can see this is one such tube. Here you can see how so many lakhs and lakhs of fibers, hollow fibers are fused together. Feed will flow here like this. Okay. And permeate can be collected here. Otherwise, it can also possible that feed can be flown here to the this one, and permeate will be collected, okay, from overall from here. Any such possibilities there, in out or out in. So, the advantages is that low pumping power, that is one of the, so it saves actually energy and the cost, and very high packing density. So, we have seen na how I just we saw that in an industrial establishment how lakhs and lakhs of hollow fibers are fused together in a single module. That means you can understand that in a very small floor space we can have so much of membrane area. So, ease of cleaning using back flushing. So, cleaning is easy here, we can use back flushing to clean the membrane as well as the module also, and ability to achieve high concentrate in the retentor. So, you can have very high concentration in the retentor. So, disadvantage is the fragility of the fiber, since they are not actually they are not actually supported, okay, they are self supported more or less. So, in this case here the fragility of the fiber is an issue. So, inability to handle suspended solids is another problem, because they are very thin, there is very small structures actually very thin. So, that is why they cannot handle suspended solids. And one of the disadvantages if you use for outside is that channeling may occur. Okay. So, channeling is something which is very much inherent to the packed bed type of reactors. The same thing may happen here if you are using a outside to in system. Okay. So, this means that the feed has a tendency to flow along a fixed path, thus reducing the effective membrane surface area. So, if we want that the entire surface of the membrane surface, whatever it is available inside the module is being utilized, then it is better to take the feed and flow it through the membrane. Okay. The hollow fiber module could be used only when the feed stream is relatively clean. That means, it is clearly understood that it cannot handle suspended solids. So, applications is that in case of seawater desalination, which is effective, but still there is some effective pretreatment is also required, gas separation and as well as pervaporation. So, now let us talk about the system design. Okay. The design of membrane filtration system can differ significantly because of the large number of applications and module configurations. So, there is no thumb rule. So, everything depends upon what is your requirement and what are the things that is available with you. So, the module is the central part of all membrane installation and is often referred to as the separation unit. A number of modules connected together in series are called or parallel are called a stage. We can have 2, 3, 4 or 6 modules together and they are connected in such a way that I can call it as a stage. So, we can have more than 1 stage, 2 stage, 3 stage. So, this is basically in series or we can call them cascade also. So, the task of an engineer is to arrange the module in such a way that an optimal design is obtained with the lowest product cost, because anyway you have to take care of the economics. And two type module operations are possible, one is dead end and cross flow, and we have discussed what is a dead end flow and cross flow in one of our previous class. Let us again quickly go through what is dead end flow and cross flow with reference to module. Okay. The simplest is the dead end flow operation. Here the feed is forced to the membrane, which implies that the concentration of rejected components in the feed is getting enhanced or increased as the time progresses, okay, and consequently the quality of the permeate decreases with time. So, usually batch type you can see how the flow is occurring here. Okay. So, in this is a module, okay, right, which is holding this membrane. So, the feed is transferred to the module and it is the module is closed, then we are applying pressure from the top side. So, the permeation it is coming here, however, the retentate is getting retained on the surface of the membrane. Okay. So, in dead end filtration the cake grows with time. Okay. So, the deposition of the cake layer is nothing but your concentration polarization layer, okay, is very faster. Okay, and the flux decline is also very faster. So, you can see how the flux is declining here, okay, and with respect to time as well as the thickness of the cake layer, that is enhanced, and both is are happening simultaneously at a very faster rate. So, the next is cross flow. For industrial application, cross flow operation is preferred because of the lower fouling tendency related to the dead end mode. Since the flow is happening above the surface of the membrane, so that is why you can see here how the feed is flowing here, okay, and this is the membrane, right. Solutes are getting deposited on the surface of the membrane. However, since the flow is continuous, so the feed itself okay, is not allowing the deposition of the solids particle over the surface of the membrane. Solids deposition will happen, there will be concentration build up. However, the rate at which they are depositing on the surface of the membrane will be much slower with comparison to the dead end filtration systems. So, the feed composition inside the module changes as a function of distance in the module, while the feed stream is separated into the permeate stream and the retentate stream, and the flux decline is relatively lower. So, we can just compare the flux decline profile. Okay. Let us say this is the dead end filtration flux decline. Okay. So, this is dead end, okay. And in case of a cross flow, the flux decline will be like this. Okay. So, this is cross flow. Okay. So, you can understand that there is a huge gap of flux decline and among the dead end and cross flow system, which is why the cross flow systems is usually preferred. Okay. So, the flow scheme in the module is one of the principal variables determining the extent of separation. In principle, two basic systems are actually used. One is called single pass system and another is the recirculation system. So, in single pass we are feeding feed from here, okay, and we get retentate here and we get permeate here, and in recirculation system part of the feed we are recirculating, actually retentate we are recirculating to the feed here. Okay. So, in a multi-stage single pass design, the loss of volume is compensated with arranging the modules in a tapered design, which is also called a Christmas tree design. Okay. So, in single pass arrangement system, the cross flow velocity to the system remains virtually constant. A characteristic of this system is that total path length and pressure drop are large. The volume reduction factor, now that is the ratio between the initial feed volume and the volume of the retentate, is determined mainly by the configuration of the Christmas tree and not by the applied pressure. So, single pass system can be applied on simple applications such as desalination. So, you can see how the single pass system. So, this is the overall feed is being fed to 4 modules here, then whatever the retentate is coming. Okay. So, they are being fed to the, so if this is stage 1, this is stage 2, this is stage 3, okay. Then they are again feed here, and whatever that is coming out here is again fed here. Okay. So, gradually the number of modules in a particular stage is decreasing, that is why this looks like a Christmas tree. We can see something like this. So, let us say two stage system. So, the second system is the recirculation system or the feed recycle system. Here the feed is pressurized by a pump and allowed to pass several times through one stage consisting of several modules. Okay, that is recirculation is happening actually here. So, each stage is filled with recirculation pump which maximizes the hydrodynamic conditions and where pressure drop over each single stage is low. The flow velocity and pressure drop can be adjusted in every stage. The feed recycle system is much more flexible than the single pass system and preferred in cases where severe fouling and concentration polarization occur, as in the case of microfiltration and ultrafiltration. So, you can see here there are two stages here, stage 1 and stage 2. Okay. The feed is being fed here. Okay. And whatever the retentate is coming, okay, the retentate is again recycled back to the feed stream, right, and we get overall permeate here. Again part of this feed and retentate is again circulated to the second stage where it is being feed here, okay, and whatever we are getting the retentate partly again recirculated to the feed stream, feed of the second stage, and this process goes on. So, we can either gradually we can have reducing number of modules or we can have saves number of modules. So, depending upon actually what is your requirement, how many stages you require to achieve your targeted separation. So, now let us discuss the different types of flow types in membrane modules. So, classically we have 4 different types of things, this one flow type that is possible apart from the dead end filtration mode. So, dead end I am not seeing because we have already discussed that, and it is not used in commercial or large scale also. So, large scale operations and flow types are basically restricted to co-current, counter current, cross flow and perfect mixing type. So, perfect mixing is completely mixed flow type. So, in co and counter current operations, the feed and permeate stream flow co-currently, which is called parallel flow, plug flow or counter currently along the membrane. So, the first case is co-current flow. Here you can see feed, okay, is being flown entering from one direction, when we get retented and permeate in the same side, and we can have a sweep. Sweep is optional, sweep is not mandatory. Actually, sweep helps in reducing concentration polarization also. So, the second was in counter current. Here feed, okay, and the sweep, they are actually entering in opposite directions. Okay. So, we get permeate in the feed side and retented in the other side. Then in cross flow system, feed is flowing across the membrane surface and we are getting permeate here. Okay. And in the perfectly mixed flow, so we can have the system mixed by using some sort of agitators, either mechanical or it can be magnetic also, magnetically driven. So, that the feed is get also continuously agitated as well as the permeate. So, the plug flow condition can be defined by so called Peclet number, which is a dimensionless number or group. So, the Peclet number is defined as the mass transferred by convection to that of the diffusion. So, it is V L by D, where V is the velocity, L is the length of the channel or the pipe, and D is the diffusion coefficient. Okay. So, if convection is dominant over diffusion, then Peclet number is much greater than unity. So, it is much more higher than 1, and in cross flow mode with perfect permeate mixing, it is assumed that plug flow occurs on the feed side, where whereas mixing occurs so rapidly at the permeate side that composition remains the same. Since we are mixing both the feed and or let us say we are agitating both the feed and the permeate. Okay. So, the concentration or the composition of the permeate mostly it remains the same. And as far as cross flow operations are concerned, counter current flow always gives the best results. Okay. So, followed by the cross flow and co-current flow. However, the worst results are given by perfect mixing. However, in general perfect mixing is done using a permeate recirculation. So, that is why it is called permeate perfect permeate mixing. So, the permeate is getting mixed continuously. So, now let us understand what is module selection and how we are going to select a particular module. So, we have discussed and understand the different types of modules that is possible, whether it is a stir cell module, whether it is a tangential system, that is plate and frame system, whether it is a capillary one, whether it is a tubular one or hollow fiber one. We have discussed so many things. Okay. Now, which one you will choose? Okay. So, the choice of the membranes is mainly determined the economic consideration. Okay. So, this does not mean that cheapest configuration is always the best choice. The type of application is also important. Okay. It is not always true that whatever is the cheaply available or which module cost or membrane cost is cheap, that only you will use. It is not so that. What is your targeted separation, that is most important. So, hollow fiber modules are very susceptible to fouling and are difficult to clean. Okay. Pre-treatment of the feed stream is most important in hollow fiber systems. So, each module configurations has its own field of application. This is very true. Okay. So, that is why after each module we have discussed that their advantages and disadvantages and where they can be applied. So, for example, hollow fiber and spiral wood modules are very useful in seawater desalination, gas separation as well as pervaporation, right. Hollow fiber and spiral wood, but I cannot use other modules here. In dairy applications, we can go for tubular or plate and frame modules. They are also very good in such food and beverages industry applications. So, if you can compare the qualities of various membrane configurations, you can understand that these are different parameters on which the comparison is based. Okay. So, we have compared tubular system, plate and frame system, spiral wound, capillary and hollow fiber. So, these are the criteria. First one is packing density, then the investment. Investment means the initial capital investment, then fouling tendency, cleaning, membrane replacement. Okay. Based on this is a comparison table you can see, and based on this you can understand that which modules to be chosen for a particular targeted separation or application. So, module designs most commonly used in major membrane separation. This table will give you an understanding that what type of modules are being used for different application. For example, you can see in RO reverse osmosis RO for actually seawater desalination, we usually use spiral wound modules. Okay. Hollow fiber modules are also possible, however, their use is restricted. So, similarly, industrial and brackish water desalination using RO, again we use spiral wound modules. Okay. Fine fibers are too susceptible to scaling and fouling. Okay. So, for ultrafiltration applications, either we can use tubular, capillary or spiral wound membrane. So, for gas separation application, usually hollow fibers for high volume application with low flux is used, okay, because the low selectivity membranes in which concentration polarization is easily controlled. So, you will use spiral wound for gas separation when fluxes are very high. Similarly, for pervaporation, usually pervaporation systems are very small, they are small units, okay, and so plate and frame systems are very good for them. Spiral wound and capillary are also being introduced recently. Okay. So, student, with this we came to conclusion of today's lecture. So, you can refer the these are the text and references, mostly it is taken from Mulder, which is the basic principles of membrane technology or our the basic textbook which I am referring for this course, apart from other references. So, the next class, which is module 2 and lecture 6, we will start discussing what are the different types or what are the different ways or techniques to prepare a particular membrane. Okay. So, basically we will learn membrane preparation techniques. So, next class we will discuss about phase inversion, evaporation, precipitation, thermal precipitation and immers precipitation techniques. Okay. So, if you have any query, you can write to me at kmohanty@iitg.ac.in, and thank you very much.